Well, for today's work, I want to address a few kinds of problems I think I'm going to be asking of you that are a little bit different maybe than some you've seen in the text. I think they are particularly useful in the particular format that I find myself and yourselves working in for this kind of an exam structure. And so I'm going to depart from the chapter 4 material for just a bit. I want to go back, and this will essentially serve as a review for some of the things we've done in chapter 3 work, and also introduce you to this little bit different style of problem so that you have a better feel for it. It becomes familiar to you and you sort of know what to do with the work when you have it. So the problem is this. Suppose we have this function, and the function is f of x is x to the third plus b times x squared. We don't know this coefficient, minus 4x plus 1. And so it says if that function has an inflection point at x equals 2, then the question is, what is the value of b? Well, depending on the value of b, this function will or will not have differing behaviors at various points in its domain. One thing we do see is that it is a polynomial, and so the only types of critical values that it or its derivatives will have will be type 1 critical values. So nowhere in this problem do we need to concern ourselves with type 2 critical values. All right, so the question is, where does this function have an inflection point? So now that requires us to know, what does it mean, or what is required for a function to have an inflection point? Well, inflection points can only occur at critical values. And since this is a polynomial, the only critical values are type 1 critical values. Well, inflection points occur at critical values of the second derivative. So we need to find the second derivative, and then we need to say, okay, at x equals 2, this has an inflection point. So if you take the second derivative, evaluate it at x equals 2, that will have to meet the requirement for an inflection point. And what we know is, for a polynomial, the inflection points, that will have to be, the second derivative will have to equal 0 there. So let's see what we have. If the first derivative, right, we're only going to use it as a stepping stone to get to the second. The derivative of f is given by 3x, this is the solution, 3x to the second, plus the derivative here. B is a fixed constant. The variable of the function is x. B is a constant, so we treat this as if it were a constant. B times 2, or just 2b times x to the first, minus 4. So there's the first derivative. However, we're interested in inflection points, so we need the second. 6x to the first plus the derivative of a linear term as you lay aside the variable, and the derivative of a constant is 0. So this is the second derivative. And we know that if we evaluate this at x equals 2, that needs to equal 0 to have our inflection point present. All right? Just because the derivative is equal to 0 does not guarantee it's an inflection point. But if it is an inflection point, that must be because a second derivative has a critical value there. And since this is a polynomial, the only critical values are where the second derivative is equal to 0. So the logic holds. And so if we evaluate the second derivative at x equals 2, we know that must equal 0 in order for it to be an inflection point. And what's left is to solve this for b. So this implies that 12 plus 2b is equal to 0. And it's not too hard to see b has equal negative 6. And so the value of b, in order for this function to have an inflection point at x equals 2, is b equals negative 6. This style of problem is very convenient for the style or the type of exam situation we're finding ourselves in this semester. And so I'll employ this at various times throughout not just this exam, but the later ones as well. So that's the example number 1, and then the next video we'll have example number 2.